Welcome to NonstopNeuron.com, where learning medical concepts is as easy as watching cartoons. Get your mind ready to be blown by another beauty of the cardiovascular system. In this video, we will start our discussion on local control of blood flow and see the mechanisms of short-term control in detail. Each mechanism that we will see is already amazing in its own unique way, but when you put them all together, you understand their beauty even more. That's why I am covering them in a single video, and I suggest you also watch the video till the end. The value you get keeps on increasing as you watch. So let's get started. Most tissues control their own blood flow, depending on the requirement. In general, reduced oxygen or other nutrient levels in the tissue causes an increase in blood flow. And when there are enough of these nutrients, there is a decrease in blood flow. For example, during resting, the blood flow to muscles is only about 4 milliliters per minute per 100 gram of muscle mass. But during heavy exercise, the blood flow can increase up to 80 milliliters per minute per 100 gram. This is 20 times higher than during resting. The mechanisms involved in control of local blood flow can be broadly divided into two categories: mechanisms related to acute or short-term control, and those related to long-term control. The acute control mechanisms respond within seconds to minutes. They exert control by causing constriction or dilatation of the arterial, metarteriole, and precapillary sphincter. The long-term mechanisms take days to weeks or even longer. They cause an increase or decrease in the number and size of blood vessels supplying the tissue. The mechanisms related to short-term control are Vasodilator Theory, Oxygen Demand Theory, control by endothelial-derived relaxing or constricting factors, and autoregulation with changing arterial pressure. Each mechanism has interesting things to learn about. The first two mechanisms respond to the metabolic condition of the tissue. Let's first see the vasodilator theory. The structures involved in microcirculation are arterioles, metarterioles, they're smooth muscles, capillaries, precapillary sphincters, venules, and cells. To keep the visuals simple, we will focus on one cell and one capillary. But keep in mind that whatever we see is happening throughout the tissue, including the metarterioles. Here, this glass of juice represents oxygen and other nutrients in the interstitium. They are used by the cells. The rain from the capillary represents the filtration, which depends on the blood flow. Now, increased metabolism, or decreased supply, causes depletion of oxygen in the interstitium. In such condition, the cells produce vasodilator substances like adenosine phosphate compounds, histamine, hydrogen ions, carbon dioxide, etc. These substances diffuse in nearby areas and reach the precapillary sphincters and smooth muscles in metarterioles and arterioles. Here they cause their relaxation. Resultant dilation increases the blood flow in capillaries. This brings more oxygen to the tissue and solves the problem. So this is the vasodilator mechanism of regulating blood flow. Next is the oxygen demand theory. This is my favorite. Among all the mechanisms, this is the simplest, and yet the most impressive one. Forget other structures. Precapillary sphincters and metarterioles themselves also require oxygen and other nutrients for contraction. So when the oxygen level falls in the tissue, they cannot contract. Or in other words, they relax due to lack of oxygen. This increases blood flow and brings oxygen. When oxygen is there, the sphincters can contract. The contraction reduces the blood flow. This constricted state lasts till the excess oxygen is consumed by nearby cells. As the oxygen level falls, the sphincter can no longer contract again, so it relaxes again, which again brings oxygen. This way, the precapillary sphincter and metarterioles undergo cycles of constriction, decreased blood flow, decreased oxygen, relaxation, increased blood flow, and increased oxygen, causing constriction again. This cyclic motion of constriction and relaxation is called vasomotion. If metabolic demand increases, the open phase lasts longer because the oxygen level tends to be less during this. Similar to oxygen, other nutrients also affect the blood flow in a similar fashion. For example, glucose, amino acids, fatty acids, etc. Even vitamins can also affect blood flow. For example, vitamin B substances, thiamine, niacin, and riboflavin are required for the oxidative production of ATPs. The ATPs, in turn, are required for muscle contraction. In the absence of these vitamins, ATPs are not produced. Without ATPs, the muscles cannot contract, so their relaxation increases blood flow. Thus, other nutrients are also involved in this mechanism. So it's more accurate to call this mechanism nutrient demand theory, rather than oxygen demand theory. But whatever we call it, this was the mechanism. So this is how the vasodilator and oxygen demand mechanisms respond to the metabolic state of the tissue. They mainly influence the precapillary sphincter and metarterioles. Remember this last statement. Metabolic control mainly influenced the precapillary sphincter and metarterioles. We will come back to it very soon. Now let's see the control by endothelium-derived constricting and relaxing factors. As per the name, these are the factors secreted by endothelium. Here we have relaxing factors like nitric oxide, endothelium-derived hyperpolarizing factor, and prostacyclin, PGI2. And constricting factors, like endothelin, and endothelium-derived constricting factor 1 and 2. Among dilators, the most important is nitric oxide. It's also called endothelium-derived relaxing factor. It teams up with metabolic control in a unique way. Earlier, we saw that metabolic mechanisms mainly influence the precapillary sphincter and metarterioles, right? But the problem is, most of the resistance to blood flow occurs upstream to capillaries, in larger vessels. So the dilatation of small vessels alone won't be that useful if the upstream vessel remains constricted. And that's where the role of nitric oxide comes in. It dilates upstream larger vessels in response to the dilatation of downstream vessels. So let's see how exactly this is done. The dilatation of downstream vessels makes it easy for blood to flow. So the speed of flow in the upstream vessel increases. This increases shear stress on endothelial cells, or in simple words, it increases the dragging of blood over the endothelial cells. This causes the bending of the endothelial cells in the direction of blood flow. Now the endothelial cells have an enzyme called endothelial-derived nitric oxide synthase. The bending of the cell stimulates this enzyme. The active enzyme catalyzes the synthesis of nitric oxide from L-arginine and oxygen. The nitric oxide then diffuses deeper in the vessel wall and reaches the vascular smooth muscles. Its half-life is only 6 seconds, so it cannot go farther anyway. In smooth muscle, we have soluble guanylyl cyclase. It's a receptor-cum enzyme. Nitric oxide activates it. The active enzyme, as per its name, converts GTP into cyclic GMP. The cGMP activates cGMP-dependent protein kinase G, or PKG for short. PKG does several activities. It inhibits myosin light chain kinase, which was helping in contraction. It also activates circa pumps, which reduces cytosolic calcium concentration. And it also activates some potassium channels. So exit of potassium hyperpolarizes the muscle fiber. All these effects cause relaxation of the smooth muscle. If you don't want to remember all the detail, just remember, nitric oxide causes smooth muscle relaxation by acting on soluble guanylyl cyclase. At the vessel level, the relaxation of the muscles results in dilation of the vessel. So the resistance falls and flow increases. This way, the dilatation of small vessels causes secondary dilatation of larger vessels, thus clearing the entire path for more blood to flow. So this is how the nitric oxide takes care of resistance in upstream larger vessels, when downstream vessels are dilated by metabolic mechanisms. Are you seeing the beauty of coordination? Apart from sheer stress, the synthesis of nitric oxide is also controlled by other factors, like acetylcholine, angiotensin II, bradykinin, etc. So that was nitric oxide, the most important dilator. Now let's talk about the most important constrictor secreted by the endothelium, endothelin. Don't worry, this one is very short. The endothelin is secreted when there is damage to the endothelial cells. It causes vasoconstriction, which prevents excessive bleeding from the injury. Thus, it plays a role in hemostasis. This checks the control by endothelium-derived relaxing and constricting factors as well, but the show is not over yet. We haven't enjoyed the beauty of autoregulation yet. As I said in the beginning, each mechanism is interesting in its own unique way, and autoregulation is no exception. This one is like the counterpart of metabolic control mechanisms. If there are changes in demand, metabolic control changes blood flow accordingly. But if there is no change in demand, autoregulation prevents the changes in blood flow. Are you getting it? See, the metabolic control is like your chef, who brings you food when you are hungry, and the autoregulation is like a watchman, who prevents anyone from feeding you when you are not hungry. Both things are important. Let's understand what exactly autoregulation is. In the video on the basics of hemodynamics, we saw that blood flow to any organ depends on pressure gradient and resistance. Controlling resistance of individual arteries allows independent control of blood flow to each organ. But the pressure is common at one end for all organs. Systemic arterial pressure, generated by the heart, is the common force driving blood flow to all organs. So the changes in blood pressure tend to affect blood flow to all the organs. But that is not needed most of the time. For example, when a person is doing exercise, the increase in blood flow is needed the most in skeletal muscles. Other organs, like kidneys and the brain, do not need an increase in blood flow. But the increased pressure tends to affect those organs as well. And this is not desirable. Not only it diverts the blood from where it is needed the most, but it also increases the burden on the heart. Moreover, unnecessary changes in other organs can impair their function as well. For example, in kidneys, this affects the glomerular filtration rate. In short, unnecessary changes in blood flow are bad. And that's why we have an autoregulation guy. It prevents changes in blood flow where it is not needed. So what actually happens is, initially an increase in the systemic pressure increases blood flow to the other organs as well. But within seconds, the autoregulation kicks in and brings the flow back towards the initial value, despite increased blood pressure. There are two mechanisms behind this. One is a myogenic response, and the other is metabolic factors. The myogenic mechanism is totally inbuilt to the vascular smooth muscles. It does not require any help from outside. The key to this is the stretch-sensitive cation channels. Increased pressure causes sudden expansion of the vessel wall, so the smooth muscles in the wall get stretched. A sudden stretch opens these channels, so there is an influx of positive ions. Resultant depolarization causes contraction of the muscle fiber. So the vessel constricts in spite of increased pressure. This reduces the blood flow, even though the pressure in the upstream vessel is kept elevated. If there is a sudden fall in the pressure, all the events happen in opposite directions and prevent too much fall in blood flow. This is called myogenic response. Another mechanism behind autoregulation involves metabolic regulation, as we saw earlier. A sudden increase in blood flow, be it due to a rise in pressure or whatever, washes out all the vasodilator substances from the tissue. Also, it brings excess oxygen and other nutrients for smooth muscles to contract. So the vessels constrict and reduce the blood flow. So this is how autoregulation prevents excessive changes in blood flow, with changing arterial pressure. We can understand its impact in this graph. It shows arterial pressure on the x-axis and blood flow on the y-axis. This is the pressure range where autoregulation is most effective. See how a large change in blood pressure is causing a very small change in blood flow. Without autoregulation, the graph would be like this. The same pressure change would cause this much change in blood flow. This shows how effective autoregulation is in keeping the blood flow within a narrow range. Yes, even autoregulation also fails with too much increase or decrease in pressure. But within the physiological range of pressure, it does a great job. So this is how autoregulation prevents changes in blood flow in those organs where it's not needed. Now you might ask, can't these same mechanisms also prevent an increase in blood flow where it is needed? Well, yes, your argument is logical. But those organs are not the responsibility of autoregulation. Remember, autoregulation is not the only regulator of blood flow. We also have metabolic factors like oxygen demand and vasodilators. In organs where more blood is needed, these mechanisms are stronger, and they override the autoregulation. Actually, it's a common sense if you think about it. If an organ is lacking oxygen, the autoregulation won't be able to cause vasoconstriction even if it tried, simply because there is no oxygen. So don't worry, the organs that really need an increase in blood flow will get it. So this was all about autoregulation of blood flow with changing systemic arterial pressure. This completes all the mechanisms involved in short-term or acute control of local blood flow. Now tell me, wasn't it amazing? We will see the mechanisms related to long-term control in a separate video. Now let's have a summary. Most tissues control their own blood flow depending on the requirement. In Vasodilator theory, we saw that lack of oxygen causes the production of vasodilator substances, which cause vasodilatation and increase blood flow to bring more oxygen. In oxygen demand theory, or nutrient demand theory, we saw that nutrient levels in the interstitium cause precapillary sphincters and metarterioles to undergo cycles of constriction and relaxation. Here, the open state lasts longer when demand is increased. When metabolic control mechanisms open small vessels, nitric oxide secondarily dilates upstream vessels too. This list. And finally, autoregulation prevents changes in blood flow in those organs where it's not needed. So, this was all about short-term regulation of local blood flow. Now, for sticking with me until the end, I want to share some behind the scenes. You know that I designed cartoon characters that fit the overall story of the concept. But while making this video, when I needed to show nitric oxide for the first time, I assigned this character to it without thinking about the context. Later, when I needed to show its synthesis, the first thought that came to my mind was a lady giving birth to nitric oxide. Once I had that thought, I could not think of anything else. I honestly did not want to show the synthesis of nitric oxide this way, but even after trying and waiting for some time, I could not come up with anything better. So I finally gave up and showed nitric oxide being delivered by L-arginine. But somehow, I am still not completely happy with it. If you can suggest anything better, please comment. Apart from this, I have kept most characters consistent with my older videos. If you have watched all my previous videos, you can recognize them easily. And finally, as you are watching till now, I think you would agree that this video is one of the best on the entire internet on this topic. So if you see less than 4,000 likes on this video, please share it with all your friends. Thanks for watching. See you in the long-term regulation of local blood flow.